So we covered model fairness measures, but ultimately one would like to mitigate the unfairness. So data bias can be addressed either before, during, or after model training. So each of these approaches are referred to as pre-processing, in-processing, and post-processing approaches, respectively. Typically, you trade off some accuracy for better fairness. So first, I'd like to cover some pre-processing approaches. First, I will cover sensitive feature removal, also known as unawareness, then fair data repair, and more recently, fair data generation. So sensitive feature removal is intuitive and easy to use, where you simply remove the sensitive attributes. However, it's well known that sensitive attributes are almost always correlated with other features. For example, even if you remove feature race, you can infer this information from the attribute zip code. So the idea is that people of similar race tend to live in certain areas. So just by looking at that area, you can kind of infer the race. Gender can be inferred by browsing history. So for example, women might prefer going to certain websites. So if you find that website in the browsing history, that's a strong indication about the gender. Income can be inferred from credit score. So if someone has a high credit score, that's an indicator that the income is likely to be high. So this is not a perfect solution. So one approach to fixing unfairness is to repair the data. So there is a way to guarantee demographic parity while preserving important statistics like ranking of data. So just as a reminder, demographic parity has the following formulations where for different sensitive groups, you want the same positive prediction rates. Now I'm going to show you the simplest example I found in this paper, and just you can think that the paper deals with a more general problem. So let's say that we have SAT scores and distributions for different genders. The red distribution is the male SAT scores, the blue is the female SAT scores. Now, let's say that we want to train a model on this that uses the SAT score to make some prediction. And you can see that if we keep the red and blue distributions as they are, then the model, if it uses a single threshold, is going to be unfair for male and female versus female, and violate this demographic parity here. And so the idea is to combine these two distributions into a unifying one while minimizing the amount of information that's lost. So here, the algorithm, it works as follows. So you first, for each female SAT score, let's say we start with the 10th percentile score. We find the corresponding male score of the same percentile. So here we're going to find the 10th percentile score of male. And then we simply average the two scores, and that's going to be the unified point of the these 2 points. And so we can produce this black distribution. And then if we train any model on this one distribution, we're going to get a fair result. And so in the paper, this approach is generalized to multiple sensitive groups and other settings as well. Now, more recently, there's been work that proposes data generation as a solution. So the idea is to generate unbiased data using weak supervision. So the input is some biased data and an unbiased data that's smaller than the biased data that we have some control on. We know it's unbiased. The idea is to train some generative model on the biased data, except that we're giving some weights on the example such that it's as if the generative model, like again, is trained on unbiased data. So then the generative model is going to generate new data that is unbiased. So the formulation looks like this. So when training a generative model like a GAN, the loss is computed, but for each example, we provide this weight. And this weight captures whether or not this example is part of biased data or is unbiased data. So the question is, how do we know that? How do we compute this weight? Well, the idea is to train a separate classifier, not the generative model, a new classifier that can distinguish whether an example is from biased data or not. So the training data is the biased data and the unbiased data, and we train this model. And so this classifier can be used to generate this weight. And so for the examples that are from biased data, for the dominant race, for example, it's going to have a lower weight, whereas for the one that's from the underrepresentative group, it's going to have a larger weight. And so any generative model that uses this weighted weights for training will produce unbiased synthetic data. So that was pre-processing. Now let's cover some representative in-processing techniques. There's a heavy literature here, but I'm going to cover the most interesting ones. So fairness constraints, adversarial debiasing, and label bias correction. So fairness constraints aims to maximize accuracy by providing fairness constraints in the objective function for model training. And it's targeted to convex margin classifiers, where this is like a SVM model where you're solving a convex problem, and also you use this notion of margin, which is the distance from an example to the decision boundary. Now, we want to satisfy demographic parity as much as possible. So remember, this is the definition. However, the problem is that this constraint is not convex. You can't add it as a convex constraint in this objective function. So the idea is to use a proxy instead, something that approximates this. So what is that proxy? Well, it is the covariance between sensitive attribute and the signed distance to the decision boundary. So I like to illustrate this proxy using this example. On the left, you can see a good case where you have this model that's classifying the circles versus the squares. Now, notice that some of these shapes are colored. So let's say these are Black people. And notice that there is no correlation between the race, whether you're Black, and being on one side of the decision boundary. So I can't tell based on your race whether you're going to be on the right-hand side or the left-hand side. Now, the second case is the bad case, where race and the prediction are correlated. So just by looking at the race, you can figure out which side you're likely to be on. This is exactly what covariance captures. So covariance is higher if this kind of thing occurs. And so if you make sure that this covariance is minimized, if you enforce the good case, then you effectively satisfy demographic parity as well. So while interesting, one limitation of this approach is that it doesn't work for deep neural networks that are not convex classifiers, but nonetheless very useful to know. Next approach is adversarial debiasing. So here the idea is to do some adversarial training like GANs. So you have a predictor that tries to make a prediction, maybe whether someone is going to have recidivism, and the output is yes or no. But then there's an adversary that tries to infer the race from these predictions. So you want to know if this person is Black or white, for example. And so these two components compete with each other, where the predictor wants to avoid leaking information to the adversary, while the adversary wants to glean as much information about the race as possible. And the key theorem for demographic parity in this paper is that if the adversary optimally predicts Z from Y hat, the race from the prediction and the predictor completely fools the adversary, it means that y hat is independent of z. So the prediction has nothing to do with the race. So therefore, this is exactly what demographic parity desires. You want to have a positive prediction rate regardless of the same rate regardless of the race or sensitive group. So one downside of adversarial debiasing and adversarial learning in general is that there is always issue of convergence. And so the training may not easily converge to a good solution. So there is a stability issue. The third approach I'd like to introduce is identifying and correcting label bias. So this is an interesting approach where the key difference is that you actually look at the trained model and then decide how to reweight the examples, and you repeat that process. So here we assume the existence of a true yet possibly biased labels. And the idea is to train a model, then use that result to adjust the example weights to minimize the bias. So there's a lot of theory involved in this paper, but I just wanted to give you the crux of the algorithm. So let's say that we have four examples here that start with the same weight, 0.5. Now, among these, there can be one or more protected groups, maybe underrepresented groups. This could be women. The second one could be Black people. So there is this formulation where we want to take the inner product of the machine learning model expressed as the function h and c, which is a constraint that captures fairness. So in this case, let's say this captures demographic parity. And so we want the inner product to be close to 0. That's our definition for satisfying fairness. And suppose that the machine learning model turns out to have a high positive prediction rate for one sensitive protected group like women, a low positive prediction rate for Black people. So in that case, the algorithm adjusts the weight as follows, where the first example is only in the women group, so it has a lower weight. And the third example, which is only in the second protected group, now has a higher weight. And the second example is in both groups, so maybe some trade-off, plus and minus occurs, and the weight doesn't change in this example. So that's how the weights are adjusted, and eventually we want to satisfy this condition. And there are theoretical results where the loss of a model trained on the weighted example is the same as the loss of the same model trained on unbiased labels. So it's as if you're training your models effectively on unbiased labels. So now I'd like to move on to the third category, post-processing, and introduce one work that fixes the model predictions to satisfy fairness. So this work was proposed by Hart. The idea is to post-process a model such that fairness like equalized odds holds. So remember that equalized odds wants the sensitive groups to have the same positive prediction rates when the label is 0 or 1. So the formulation is as follows. I'm just repeating one of my previous slides. Also in this paper, the authors deal with another fairness measure called equal opportunity, which is a variant of equalized odds, where A is either just fixed to 0 or 1. So now I'm going to go through the simplest solution that's proposed in this paper. Suppose that we train a model C, and the assumption is that we can no longer fix this model. So it's a black box, we can't fix the data, the model, so we have to just modify what the model is doing. So pictorially, let's say that we have this, this diagram. So the x-axis is the probability of the positive prediction rate. Given a certain sensitive attribute value, and given that the label is 0, and let's say that the y-axis is the positive prediction rate when y equals 1. So C is going to have some value, some probability of some positive prediction rate given y equals 0 or 1. So it's going to be somewhere in this space. So let's say this is that point. This is where C is. Now we're also going to cover 3 other trivial models. One is a model that always returns 1. So this model is actually the top right point here because the probability of y hat being 1 is always 1 for both the x and y axes. So that's this point. Then we also consider a model that always returns 0. So in this case, the probabilities that are always 0. So this model is this point on the bottom left. Now we also consider an inverted model of C, which simply makes the opposite predictions of C. So I'm going to denote that as 1 minus C. And it's going to be around here, opposite against the diagonal here. And now the idea is that we can combine these 4 models in some random fashion and to come up with a model that has whatever positive prediction rates we want, as long as that model is within this gray region. We can't generate a model beyond this region because it's not a combination of these 4 models, right? So in this area, we can at least come up with any arbitrary, any model that has this specific positive rate, this specific positive rate, okay? Now, we can do that for the case where z equals 0 and z equals 1. So we're going to have 2 of these parallelogram regions. So one for z equals 0, like this one, and for one for z equals 1. And they're not going to be the same regions. So there's going to be some overlap, some non-overlapping region. Now, the idea is that we can select any point in the intersecting region, and it's guaranteed that we can train a model that satisfies equalized odds. Because if we find any point in this intersection, we know that its positive prediction rate for y equals 1 is this value, right? And the same model also has the same positive prediction rate for when z equals 0 and z equals 1, because it's this point for both cases. So this means equalized odds is satisfied in the case where y equals 1. Now, we can't select the point beyond the intersection because here we cannot come up with a model that has the positive prediction rate that we want for z equals 1, and likewise for this region. And so we need to choose a point in this intersection. And which one do we choose? Well, we want to choose the best model that has the lowest expected loss. So how do we figure that out? Well, notice that the ideal point for a classifier is to be on the top left, where if the label y is 1, we want the prediction to be 1. So this should be 1. When the label is 0, we want the prediction to be 0. So we want to be 0 in the x-axis. So top left is the ideal point. So we're finding the point that's closest to this ideal position. So therefore, the red dot here is going to be our choice. The classifier that satisfies equalized odds and also has the lowest loss as well. And there are other variations of this method in the paper as well. But you can see that we can arbitrarily modify the model to satisfy equalized odds. So in summary, measuring fairness is not enough. So we also need to mitigate unfairness. And mitigation can be done before, during, or after model training. So pre-processing is useful when training data can be modified. in-processing is useful when the training algorithm can be modified, and post-processing should be used when we cannot access either the data, both the data and the model. While the bulk of the research has been focused on in-processing, recently we're starting to see more pre-processing techniques as well.